Hello, universe. So welcome to another installment of Cosmos from Your Couch. The stream has officially started. So to get rolling, let's start with my title slide to give you a little bit of an introduction of who I am and what you'll be hearing about for the next little while. My name is Katie Brevik. I am a postdoctoral fellow, which is what you do in between hopefully becoming a professor and getting a PhD. You can see the title of the slide is Whispers from the Cosmos. Hopefully by the time that I'm done, y'all are going to understand why I called it Whispers from the Cosmos. Normally when you think about space, you don't think about hearing anything, but hopefully you'll get it. So I am a postdoctoral fellow. I work at the Canadian Institute for Theoretical Astrophysics, or CITA. That's what you can see in the bottom left-hand part of the screen. If anything that you see or hear today from what I am talking to you about makes you like freak out or like think about this for days on end and you still have questions, please, please, please use my Twitter handle, SpacetimeKatie, to ask any and all questions related to space that you have in the future. Okay, just so that we're all on the same page here, these streams have roughly a 30-second or so delay. So to mitigate a lot of confusion on my end and on your end, what I'm going to do is give you a little bit of a plan for how this is going to work. So the plan for tonight is I'm going to try to answer these three questions: who I am, and why don't I understand how stars work, even though I do this professionally? What even is general relativity or a gravitational wave? And what have we learned about stars from gravitational waves? So at each of these points so I'm gonna talk about each of these questions in my talk, and after I give what I think is an answer to these questions, I'm going to actually pause and I will check the chat. And then I will answer all of the questions that have come in from the chat. So at any moment, if you have a question, please type it in the chat. Know that I'm not ignoring you. Know that I will check the chat at very regularly spaced intervals throughout this evening so that I can answer all of the questions that you have. And that way nobody gets left behind and I don't get super confused or any more confused than I already am with YouTube stuff. So thank you for joining me. Thank you for coming along for the ride. And huge thank you to the Dunlap Institute, who have sponsored this type of thing so that I can come out and connect with y'all about space and gravity. Okay, all of that aside, let's get rolling. Let's talk about what I am, what I do, who I am, and why do I not understand how stars work. So to get this going, first things first, this is where I grew up. This is a beautiful mountain called Mount Olympus. It honestly probably looks a lot like this today because I heard that it recently snowed. So if you look down at the base of where all the trees are in the bottom right corner, that's basically where my house is. This beautiful mountain range, or mountain, part of the mountain range called the Wasatch Mountain Range, is in Salt Lake City, Utah. So I am from the United States, even though I work here in Canada at the moment. And luckily for me, I'm from one of the United States where it's very easy to draw a state with just a few lines, Utah. So the star is Salt Lake City, Utah. I grew up there, went to high school there. And it turns out almost every single weekend of my life growing up through high school, my wonderful family built a cabin on the east side of this blue lake that you can see up at the top. And that lake is called Bear Lake. So here's a picture of what Bear Lake looks like from the cabin that we built. Huge thank you to my family for building this wonderful cabin that we all chipped into to have and go visit. It was like a total social life killer for my entire history of growing up, but we paid for it with the beautiful views that you see here. Now, if you turn and you look back towards the mountains, this is what Bear Lake looks like. So when people ask me, how did you become an astronomer? How did you know that you wanted to be an astronomer? I kind of like to basically show them pictures like this and say, I sort of didn't really have a choice in wanting to become an astronomer because I spent nearly every weekend looking up at a sky that looks exactly like this. And in fact, my family cared so much about sort of imparting to us that the sky is important to look at and to pay attention to, that every weekend before we could unpack our car and go in and go to bed, to get up early to start building our cabin, everybody had to stand outside and watch the sky until a shooting star came by. And my dad is hilarious. And because he wanted us to stand outside longer, there was a rule that it didn't count unless more than one person saw it. Little did I know that was actually a pretty good way to learn about scientific principles, because if other people can't prove that you saw the thing that you say that you saw, then it's not really verifiable. So thanks to Dad for that one. So anyway, I literally spent the first 18 years or so of my life every single weekend looking up at stars like this. Now, I'm not the only person who has thought to look up at the stars and wonder what they are doing, why are they up there, how do they work, what the heck is a star, all of that. People have been looking at the stars for literally as long as we've had eyeballs, right? Like we've been looking up, we've been thinking about our place in the universe, thinking about what all of these bright points are. In the 1600s, Galileo pointed telescopes and looked at the stars and could see that the stars were still tiny, tiny points of light. So we've been studying the stars like academically, scientifically for hundreds of years, and we still don't totally know exactly how they work. And there's one really, really crucial reason for why that's the case. And that crucial reason is because stars evolve incredibly slowly compared to the way that we humans here on Earth evolve. So as an example, I want to show you a video of one of my favorite stars. One of my favorite stars is called Eta Carina, and it is this enormous star that actually is a pair of stars. So there are two stars that we think are orbiting each other. Now, we obviously don't see these stars in the inside of this big nebula of gas. However, we know something's going on there because it's pretty weird looking. And so astronomers petitioned the Hubble Space Telescope, my favorite telescope because it launched the year that I was born in 1990. They petitioned the Hubble Space Telescope to watch Eta Carina and this nebula that surrounds these stars. And so the Hubble Space Telescope checked in 1995, 2001, and 2008. And that's what you see in this picture. So this is actually a movie of those three images over time. And you can actually physically see the gas, like this explosion expanding. And you can tell that it's not a trick because in the upper left-hand corner, there are two stars that are perfectly centered. Not centered, that's not right at all. They're perfectly stationary. And so because they're stationary, you can actually use them as a reference point and say, okay, I know that these two things are stationary over these 13 years. This gas is actually expanding. I think that's super cool because usually in astronomy, we don't have videos like this. Stars don't evolve fast enough for us to take videos. To put this into perspective for y'all and for myself, this is what was happening according to me from 1995 to 2008. Huge thanks to my mom for allowing me to credit her for these wonderful images. So in 1995, I started kindergarten, and in 2008, I graduated high school. An enormous amount of stuff happened for me in those 13 years. For Eta Carina, it's like just about ready to like let out a sneeze, we hope, so that we can watch the explosion happen. But whether or not that takes 10 years, 100,000 years, a million years, our theoretical models actually aren't good enough to tell us on human timescales. So if you're a person like me who loves the stars, who cares about the stars, if you have questions about Eta Carina, by the way, put them in the chat. I'm going to check on it in just a little bit. just a quick aside there. So if you're a person like me who cares about these stars, who loves them, wants to study them, you can't do it over the course of your lifetime because stars just evolve way, way, way too slowly for us. Our sun will evolve for another 5 billion years past the 5 billion years or so that it's already been evolving. No humans are going to be around for that long, at least unless we have a big chain of scientists continually keeping records. And of course, we're doing that. There are, of course, other ways that we are studying the stars. And because us astronomers don't want to wait millions or billions of years for things like Eta Carina to blow up, or other types of stars like our sun or Betelgeuse or any star that you can think of, because we don't want to just wait and watch, we have to get clever about how we do this. So one way that we get clever is kind of the same way that we actually study humans. And fun fact, if you're in the United States, this is happening now. So please sign up for the US Census if you can. It's a really, really important thing to do. Just to count and study humans. That's literally the point of this, right? To understand what's going on. Just the same way that our governments take a census of the population and they study and they say there are this many young people and this many old people, we look at the stars and we take a picture, like the picture that you see here. And based on this picture, we use what we have to observe. The thing that we have to observe here is the color of the stars. Blue stars are younger because they're hotter, and red stars are older and cooler. And because we know that there are red stars and blue stars and yellow stars in the middle, we can actually start to piece together kind of like, okay, this is a population. And if you have this many old stars, so you have 100 old stars and only 5 young stars, then it can tell you that the age of that population is really, really old, and most of the stars formed a long time ago. That's extremely helpful. I have tons of colleagues who do this, and it's a beautiful way to study the stars. There's another way that you can study the stars. Little car in the background. Love streaming on YouTube. Okay, so there's another way that I personally love to study the stars, and that is to study the relics of all of the stars that came in the past. Now, in the same way that if you only take a census today, you only know what's going on in the world in 2020, because that's where we are. That's when we took our data. That's what the census is. However, if you want to tell the story of humanity, you want to have the perspective of all of the wonderful things that humans have done in the past, we look to our ancient relics of civilizations in the past. And because we have these relics, because they stick around for a long time, we can piece together our history, which is really important to informing why humans are doing what they do now. This principle is exactly the same for stars. Every star that lives will turn into one of 3 things. It will turn in, if it's like our sun, it's kind of a little like mediocre, regular, nice, easy to live around star. It will end its life pretty quietly and slowly as something called a white dwarf. And that white dwarf will eventually no longer be able to fuse elements. And so it will just be a little hot ball that will slowly cool over time. And as it cools over time, it gets less and less bright. Now, if the star is something like 10 times the mass of our sun, it will explode in something called a supernova, some of the most explosive things that happen in our universe. And those supernovae will leave behind a neutron star. A neutron star is a star that's roughly 10 or so kilometers on its side and is pretty much a ball of neutrons or close to it. That thing is going to be incredibly dense. And yeah, neutron stars are totally wild. If you have questions about them, definitely ask me in the chat or tweet at me or whatever. Sometimes it's really hard to think about neutron stars because they're confusing, and I find them confusing as well. But let's get back to the other stars. So we talked about a solar type star that's going to turn into a white dwarf. A neutron star is going to come from a 10 solar mass type star. And then things that are like 20 solar masses or bigger, 20 times bigger than our sun, that's a really big whopping star. That's going to eventually probably go through an explosion like a supernova, and collapse forever. And that collapse forever leaves behind a black hole. So every star that ever exists is going to leave behind a white dwarf, a neutron star, or a black hole. And these are our relics that we can look out into the universe for and study them. So if you want to study these types of things, that's a little bit difficult because you'll notice, specifically, the good example here is the black hole in the bottom right. The definition of a black hole is something that is so dense that nothing can escape it, not even light. As an astronomer who points telescopes at stars, black holes are really, really, really flippin' hard to find because they don't emit light. And white dwarfs emit a little bit of light, but not a lot. Neutron stars basically only emit something called radio waves. So if you're trying to find dead stars, telescopes really aren't going to do it for you. So in order to study them, you have to think a little bit more carefully. Okay, so next step, we're going to stop for question time. And I'm going to look at the chat. There have not been like a ton of questions. Oh my God, one question just came in. Yay. Okay, so first question. What is the diameter of the largest neutron star before reaching the critical mass that it would turn into a black hole? So the interesting thing about neutron stars is that they can't have like an enormous amount of mass between them. The mass range of neutron stars that we think exists is something like 1.2 times the mass of our sun, up to like maybe 3 times the mass of our sun. That's not a big range. And so if you take a big old ball of neutrons, you pack it in to make a neutron star, the size of that star is only going to be between 10 and 20 kilometers on a side. It's not going to get much bigger or much smaller. That's kind of weird. The other thing that's super wild about that is that we know how big that is because there are nuclear physicists who live here on Earth. They didn't go to a neutron star. They just know from nuclear physics, from stuff that we can test and see here on Earth, that that's how big neutron stars are, because we know what neutrons are. Science is awesome. Okay. And I think I answered that question. Cool. All right, so there are no other questions currently. If you didn't have time to get a question in and you're like, oh, I still have a question about stars, please still just copy them into the chat. Would love to have them. We're about to rip off into the next question, which is what even is general relativity or a gravitational wave? I suspect that we're gonna start getting a lot more questions because that kind of stuff breaks my brain the same way that it breaks everyone's brain. So get ready to break your brains. All right, let's get rolling. Next part. We're going to go to everyone's favorite cool Uncle Albert of the guy who does gravity, right? Okay, so whenever anybody thinks about gravity, we think about Einstein. Some people who have been in physics classes in high school maybe think about Newton. We'll talk about Isaac Newton in a minute. But really, when the universe thinks about gravity, they think about Einstein. And if you want to think about general relativity, you got to go to the source. That's Einstein. But before we get there, let's start with something a little bit earlier. So in 1905, Einstein wrote down a theory called special relativity. For any of you who have taken a physics course and had to work through special relativity questions, I apologize. They're hard. They're really hard for me. They're really hard to teach, but they're super cool. Now, if you haven't done that before, that's totally fine, because what we're going to take from this is just one tenet of special relativity, and that is that nothing can travel faster than light. Einstein wrote this down in 1905, and he thought about it. He had to think about it a lot. And he had one realization as well with this, which is that gravity can't even travel faster than light. He had this theory that said nothing can travel faster than the speed of light. And this theory explained why all of electricity and magnetism worked. So it's probably right, especially because I'm talking to you through a computer that relies on this stuff. So we definitely know Einstein was right with special relativity. And so as he was thinking, okay, nothing can travel faster than the speed of light. not even gravity. And that was really perplexing. And so he thought about a wonderful thought experiment that we're all going to do together. So in this thought experiment, Einstein thought about the Earth going around the sun. This is the picture that I could come up with the Earth going around the sun. So Einstein thought about the Earth, it's going around the sun. We know from Isaac Newton exactly how the Earth goes around the sun. Very simple. Newton's laws of gravity, they work beautifully to explain this. So Einstein's thinking about the Earth going around the sun, and he thinks, okay, what happens to Earth's orbit if the sun suddenly disappears? Now you can see here that the Earth is whipping around the sun. That's probably not what's going to happen. So I'm going to pause it and we're going to think for a second here. Now, if there is no sun, that means that there is no gravity. There's nothing that's pulling the Earth along to tell us where the sun is going, or sorry, where the Earth is going. Since the sun isn't there, the Earth actually, according to Isaac Newton's laws of gravity, will just shoot off in the direction that it was headed before the sun disappeared. Now, that sounds pretty reasonable. If you write that down in a physics class in high school, you're probably going to get the question right. However, think back to what Einstein had thought about in 1905. Nothing travels faster than the speed of light. So if you're sitting on the Earth and the sun suddenly disappears, how soon do we here on Earth know that the sun is gone? Now, for those of you, normally if we were like in person, and I wish we could be in person, but we are not, I would ask, how soon does Earth know? And of course, there's always wonderful, wonderful people who know the answer right out the gate. That answer is, of course, 8 minutes. And that's because the light from the sun, the very last bit of light that leaves the sun before it disappears, is going to take 8 minutes to traverse the distance between the sun and us here on Earth. Now, hold on a second, though. Take a step back. I just told you that the Earth would take off immediately. And according to Isaac Newton, the guy who invented calculus, this is true. The Earth would take off immediately. But that totally breaks Einstein's theory of special relativity. That says that the Earth would take off instantaneously, the light would take 8 minutes to reach us, and that means that the gravity that the sun had that was causing Earth to orbit had traveled faster than the speed of light. Yikes. That's a rough start to a theory of special relativity. So Einstein decided that he needed to solve this problem. As every good physicist and scientist does, if you come up with a theory, you must describe not only how your theory works, but how it either disproves every theory that came before you or proves that it was correct. You have to build incrementally and make sure that everything checks out. That's one of the things that's fantastic about theories in science, is that we actually prove and show our work. So Einstein does this. He does this for 10 years. He works, and he comes up with this beautiful, beautiful geometric idea. Shout out to my friend Carl and the people at Northwestern where I did my PhD. They made this beautiful visualization that we can all watch together. This visualization shows what Einstein came up with. And that is called the theory of general relativity. So instead of thinking about equations, which of course are in the theory of general relativity, Einstein just kind of thought about geometry and what is gravity? And this is what he came up with. It took 10 years and it's like beautiful. If you meet me in person, I will gush about this just like I'm gushing about it to you now. If you meet a lot of people who do the kind of stuff I do, they will totally gush about how beautiful this theory is. And it's because we can describe it so simply. The way that we think about general relativity is that every object that has mass, every object in the universe actually, lives in space-time. That's what we're showing with this grid of lines that you can see. If that makes you like kind of want to fall down and be stressed out, the thought of space-time, I share that completely with you. I usually just think about space. So I'm just going to say space, even though space-time Katie is my Twitter handle, whatever. We're just going to talk about space. So every object is in space, and every object that has mass causes space to curve a little bit. That curvature in space is what we understand as gravity. That curvature is what causes us to feel gravity. There's a really nice way to say this, which is that objects that have mass or matter tell space how to curve. And because that space is curved, it actually tells matter how to move, like you see here. So in this image, what I'm showing is sort of like a picture of a really dense, maybe bowling ball with a little smaller bowling ball that has less mass. It's orbiting. It's orbiting in the orbits and the circles that Isaac Newton's theory came up with, but it actually explains why that orbit happens. That's why everybody is obsessed with general relativity, myself included. Okay, so this is how gravity works. This is what gravity is. We're just gonna whip right through. Everybody gets an A in general relativity from Dr. Katie. Cool, cool, cool. So if anybody asks you, it's literally just gravity is curvature in space. Great, that's general relativity. Now, if you stop to think about this for a second, and you think about like, okay, like this is like bowling balls on a trampoline. Now, if I chuck a bowling ball across a trampoline, that trampoline is gonna react a little bit, right? Like you can't just have really, really dense objects going around each other in space and not do something to the space. Space is sort of like this sheet. And it turns out this is what happens in the universe. Like there are actual ripples in space, ripples in time that happen. These are called gravitational waves. And they basically kind of do what you see on the screen here. They cause space to stretch and shrink. The thing that's so cool about gravitational waves is that they literally fall out of Einstein's theory of general relativity. The same way that if you write a theory down about electricity and magnetism, we just see how light is emitted from the equations. If you write down the theory of general relativity with equations, you can actually see this idea of gravitational waves, which are just very similar to light waves emitted from the system. If that makes you feel like you need to ask questions, please ask them in the chat. I'm not getting a lot of questions, which makes me feel either very positive or very negative. So please validate me and ask beautiful questions or not beautiful questions in the chat. Okay, cool. Break is coming up soon. Let's get rolling. So this is what gravitational waves are. They are ripples in space and time. They're predicted by Einstein's theory of general relativity. What do? They actually physically stretch and shrink space. So if you think about a gravitational wave traveling out of your computer right now, and you have these dots that I've provided for you, this is exactly how a gravitational wave stretches and shrinks the space. We can write this down because of Einstein's theory. The thing that's beautiful about this is that we can predict exactly how the ripples stretch. That's very important because to have a prediction means that you can test that prediction. That's one of the best tenets of a theory, is a prediction. So Einstein's theory of general relativity predicts that gravitational waves will stretch and shrink space in exactly this type of predictable way. Okay. So in 1916, Einstein wrote down a paper. The way that we actually do science today, he wrote a paper, he wrote it in German because he was German. Most papers these days are written in English, but he wrote down a paper to tell the world that gravitational waves probably exist. And he had done some calculations, and those calculations told him that they are way too small to detect in the year 1916. How small are the ripples that I showed you? The ripples stretch space by a factor of 10 to the minus 21. Okay, so some of us have like done scientific notation. If you haven't done it before, don't worry. Scientific notation stresses me out sometimes too. This is actually what 10 to the minus 21 is. It is a 0, a decimal point, and 21 zeros. What? Okay, what does that even mean? Like, what is 10 to the minus 21? Let's put it into some context. If you wanted to stretch a meter by 10 to the minus 21, it would shift by 10 to the minus 21 meters. I'm basically a meter. Actually, I'm kind of like 2 meters, a little closer to 2. Let's make it way smaller. What's the size of a hair on my head? The width of a hair? Something like 10 micrometers, or something like 10 to the minus 5. That's really small when you think about it. Let's go even smaller though, because we're not even close. We're not even close to 10 to the minus 21. Let's take it down to the size of a nucleus. The size of a nucleus is like 10 to the minus 15. Okay. That's the smallest thing that exists, that we know of, that we are built out of. All matter is built out of these atoms and nuclei that are 10 to the minus 15 meters. That is 1,000,000 times bigger than what gravitational waves do to stretch space. So if you're Einstein, it's 1916. You're going to write that paper. You're going to do some calculations. You're going to say there are maybe black holes that exist out in the universe. I'm going to calculate how strong they are when they deform space and they reach us here on Earth. And that is too small to detect. So he wrote a paper that said we will never detect gravitational waves. Einstein is usually not wrong about a lot of things. So for a long time, people were like, cool, cool, cool. I guess this is done. We don't have to worry about finding gravitational waves. There are other ways to test general relativity. Let's move on. If this makes you have questions, please ask them in the chat. Okay, because I'm ready to answer questions. Yay. All right, so I'm going to check the questions. We have one, which is, how can we tell that gravitational waves actually exist? Ooh, buckle up. That's what the rest of this little YouTube session is going to be about. And spoiler alert, we all live in the future. We have detected gravitational waves. Yay. Okay. If there are no, I'm going to like hang for just a minute to make sure, because I know that there's a delay here, to see if any other questions come through. You can also ask me questions like, what are your cats' names, if you want. I don't really mind. You can ask me how the weather is in Toronto. Spoiler alert, it's gray today. Too bad. Cool. Okay. I'm not seeing any questions yet. This is wild. Usually people see something like general relativity and are like, oh, what does this mean? But maybe we'll get there near the end of the talk. So for the next little while, I'm going to tell you what we have learned from gravitational waves. And to do that, I'm going to explain first how we detect them. So currently, we have 3 detectors that were, until very recently, online looking for gravitational waves. This is the Laser Interferometer Gravitational Wave Observatory, or LIGO. That's the 2 that you can see on the left. And then we have the Virgo interferometer, which you see on the right. Notice that I'm using the word interferometer. That's kind of a weird word. We'll talk about what an interferometer is in a second. The other thing to notice, if you weren't weirded out by me saying interferometer, is that these don't look like your average telescopes. Now, why on Earth, if we're astronomers, are we not using telescopes? The reason for that is because we are detecting gravitational waves. We are detecting light. Oh my word. We are trying to detect gravitational waves. We're not trying to detect light. So we can't use telescopes to do this. We're trying to find black holes out in this universe. So we better use what we understand about gravitational waves. Okay, so if we know that gravitational waves stretch and shrink, they make us stretch and shrink like this, we're going to build detectors that are big L's, like you see, because we want to measure space literally stretching and literally shrinking in real time. That's what these detectors are designed to do. They are 4 kilometers-ish on a side. The one that you see with all the trees around it, that's in Baton Rouge, Louisiana. The one that you see that looks like it's kind of in the desert is in eastern Washington state. And the one that has beautiful farm fields and probably is growing delicious, wonderful wine for somebody up in those mountains is in Italy. Okay, so these are our interferometers. These are our gravitational wave detectors. Now, how do they work? Thankfully, the folks in the LIGO collaboration have made a video to explain to you why these detectors work and how they are able to measure stretches and squashes in space that are roughly the size of 1,000,000 times smaller than an atom. The reason that this works is actually through something called lasers, which you may have heard of. We use lasers maybe not everyday life. Scientists use the heck out of lasers in their everyday life. And the whole reason that these detectors work is because you can take laser light and you can split it with something called a beam splitter. Now, if you've designed your detector to have two arms that are exactly the same width, then that light will come back, it's split, and it will cancel. And if you look at your detector, the light has perfectly canceled. Now, if you stretch the arms, even by 1,000,000 times smaller than an atom, the amount of time that it takes the light to travel from one end of the arm to the other will change. And that's going to make these light waves interfere and produce a signal. This idea came about in the 70s, which is like a way long time ago when you think about it. I grew up in the 90s, so I'm like, okay, cool, like the 70s are 20 years ago. No way, girl. Way longer than that. It's 2020. The 70s were 50 years ago. So we've been thinking about detecting gravitational waves with lasers for 50 years, which I think is fantastic. Okay, so this is how LIGO works. LIGO is just a big old ruler, effectively, that shoots lasers from one end of an arm and another end of an arm down and back. If a gravitational wave comes through, it jiggles, makes the light interfere and show up. Great. Okay, now everybody, this is where things get really exciting. I told you, I spoiled it already. We live in the future. These detectors freaking work, which is awesome. Super awesome for people like me who depend on this type of stuff for their livelihood. So let's take a step back and look at this beautiful, beautiful image. This is two black holes. And now we're going to start playing a movie. Over 1 billion years ago, these two black holes were orbiting each other, probably in a galaxy super, 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 super far away. Here on Earth, like microbes are forming. These black holes, I call them binary because there's two of them. That's actually like a fun astronomy word. They're orbiting each other. And as they orbit each other, they're emitting gravitational waves. As they emit gravitational waves, they get closer together. Okay, so I was yapping. We're going to talk about this more. I was getting all excited about how long ago it was. Okay, so we're 1 billion years ago. Black holes are orbiting each other. They're emitting gravitational waves. These gravitational waves carry energy, so the orbit shrinks. It turns out that the closer the black holes orbit each other, the more the gravitational waves are emitted. And so this like runaway process happens, and it causes the black holes to merge. Eventually, they will crash into each other. And as they do this, they emit one huge burst of gravitational waves. And you can see the space kind of like people. Okay, so the gravitational waves that come from those black holes, they travel across the cosmos towards us for 1 billion years. 1 billion years minus 50 years ago, somebody figured out how to make a detector to find the gravitational wave that comes through. They petition the National Science Foundation in the United States and science foundations in Italy and Europe to build the detectors. They figure out how to build the detectors. They turn on for something called even a science run, it was a test run, but they're on. It's September 14th, 2015. I'm like not 2.5, 2 years into my PhD at Northwestern. I had been told by somebody that I was throwing my life away by trying to study gravitational waves because we would never find them, which is hilarious at this point in time to me. So it's September 14th, 2015. We have our two detectors, LIGO Hanford, which is in Washington, and LIGO Livingston, which is in Louisiana. And this is the signal. Okay, I'm gonna actually try to turn up. I hope that this sound plays for y'all. Please tell me in the chat if it doesn't, and I'll check. It's gonna play again. So that little signal comes ripping through the detector. And the detector, in time, you can see down on this x-axis that it was about 1/2 second. Really, the signal was only observable for about 0.2 seconds. And then on the y-axis, you see the frequency. The frequency is how fast the wave is going. It turns out that because the black holes are causing the ripples in the gravitational waves, that excuse me, that frequency tells us how fast they were orbiting. So the black holes were orbiting each other at the very end there, almost 500 times a second. What? The black holes were orbiting each other. A 30 solar mass black hole was orbiting another 30 solar mass black hole 30 times, or 500 times, 30 times, what? 500 times a second before they crashed into each other, emitting these beautiful gravitational waves. Now you'll notice that there was sound. That's a thing that I pointed out that I wanted you to think of. The sound that you're hearing is actually the sound of what a sound wave would have at that frequency. Now I want to be super clear. Gravitational waves do not play sounds. They stretch and shrink space. There's a lot of fun debates about whether or not our ears can hear gravitational waves if they were at the right frequency. But that's not what I'm getting at all here. What we're doing is we're taking the data that you see, the line underneath the big swath. We're taking that data. It's kind of like a sound wave, and we're sticking it into an audio interface. And this is what we hear. It's a little bit low the first time. This is why I call this whispers from the cosmos. This is because if you take data from gravitational waves and you stick it into headphones, you can hear black holes crashing into each other. What? Super cool, super fun. Okay, so September 14th, 2015, two black holes, well, minus a billion years, two black holes crashed into each other. A billion years later, we found this in two detectors. The reason that we believe this signal and the reason that we believe that gravitational waves exist is because we had a prediction. We knew exactly what the signal should look like. The signal matched so perfectly that you see here, and we saw it in two detectors. That's the only way that you could ever convince any reasonable scientist that this type of thing is real. Okay, let's keep going. We're gonna rip going. I see one question in there and I want to answer it so bad, but I have to force myself to answer during question time. The last question time is actually going to be a little bit later on, so I hope lots of questions start rolling in because this is just one of many, so buckle up, friends. Okay, now, the LIGO detectors and the Virgo detector turned off for a while, and then they turned back on. You'll see there's all of these waves that you see here. So in 2015, so okay, slow down. I'm getting all excited. And I just want to explain to you so fast how we name gravitational waves because I love them. Okay, so we have a G and a W in front of every single one of these squiggly lines. That stands for gravitational wave. Now there's one that doesn't have that. It has an LVT. That stands for LIGO Virgo trigger. The reason that doesn't have a GW in this plot is because our data analysis wasn't good enough at the time to classify it as a gravitational wave. Now that it's 2020, we allow the beautiful orange squiggle to be a gravitational wave. That's fun, love that. Join the gravitational wave family. So each of these types of gravitational waves have different signals. These are all pairs of black holes that crashed into each other. The first one came in on September 15th, 2014. That means that it came on the 15th, that's your 1-5, of September, 09, in 2014. Oh man, have I been saying 2015 the whole time? Probably. Dates are hard. Things really start to go together after a while, huh? In any case, this is called GW 150914. That's the date that we detected it. That means that we discovered other gravitational waves going down the line on October 15th. Oh, wait. Oh man. Yo, YouTube is hard and doing stuff live is hard. We're gonna do this one more time. 15 is the year. September is the month. 14 is the day. That means that October 12th, 2015, we found another one on December 26th. That's like the time at Greenwich Mean. This actually came through the United States on Christmas. It was like a Christmas Eve or a Christmas present. Then we turned off our detector. You see that there's a gap from 15 to 17. They actually turned off the detectors did some upgrades, made the lasers work really well, like made the mirrors that we bounce the lasers off work better, things like that. And then they turned on again in 2017. They found 2 more black holes crashing into each other on January 4th and on August 14th. And then another signal came through. Now, as this signal comes through, this is going to play a movie. And what you're going to see is the same type of wiggle over time, but the x-axis below that shows the time is actually going to start moving, and it'll show you how long this signal lived in the detector. The other thing that you'll note is that the wiggles are not as tall. So this is very obviously a different kind of signal. This is not 2 black holes crashing into each other, because they orbit around each other for like 0.2 seconds, maybe 2 seconds before crashing into each other. This signal came whipping through, and it's going, and it's going, and it's going. And it's small in our detectors, but because it has a very predictable shape and it just keeps going and going and going, we can search for this kind of signal and watch it build up in our detector. And it keeps going and it keeps going. What this tells us is that the objects that are causing these gravitational waves are orbiting each other many, 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 many more times than the black holes that crashed into each other that we had previously seen. It also makes a different noise. It makes a higher pitched noise because they can get to higher frequencies. That's fun and interesting and exciting. The reason for that is because the size of the objects is smaller, so they can orbit each other faster before they crash into each other. Now, if you are not a gravitational wave astronomer, you're like, okay, cool. We understand that the height of the squiggle is smaller, so maybe it's not as strong, but it goes longer, so we can build it up in our detector more. And the frequency of the sound was higher. So that means that the frequency of the wave was higher. What are these things? Maybe you don't know. A gravitational wave astronomer is like, yo, we got neutron star merger instead of a black hole merger, which is awesome. Why were we excited about a neutron star merger more than a black hole merger? Well, some people were. I'll be honest. I still like black hole mergers more, but there are people in this world who are obsessed with neutron star mergers. And the reason for that is because neutron stars are made of matter. Because they're made of matter, you can see this is kind of like a picture of these 2 neutron stars. They're coming in, they emit gravitational waves, like we saw the signal for, but when they crash into each other, they cause a mighty explosion, like you see here on the screen right now. This explosion emits light in literally every single wavelength. It emits light from gamma rays all the way to radio waves, which is awesome if you are an astronomer who points telescopes at the sky, because you can see the light. Okay, we're going to do this one more time, and I'm going to explain to you exactly what kind of light that we're seeing. So before they crash into each other, no light, just gravitational waves. They're orbiting, they crash into each other. Boom, there's a big old jet that emits gamma rays and then X-rays. Now, this big cloud of dust, this is all this matter that is decaying, doing nuclear decay and emitting light that optical telescopes can see. And as the jet from the neutron star, whatever it's called, explosion, merger, sends out, it also then starts to emit UV, X-ray, as I said, gamma rays, and radio. So we can observe this merger to exquisite precision. And it turns out that astronomers did that. They wrote papers about this. It was definitely one of the most observed objects ever to exist on the planet. They wrote scientific papers that had like 3,500 authors on it. Can you imagine getting 3,500 people to agree on anything? It was a trying time, but everybody was super excited, and it was totally worth it because we learned so much. Okay, let's keep going. So at the end of 2017, these were all of the things that LIGO had seen. Now in purple and in yellow, this, sorry, when I say LIGO, I should really say LIGO Virgo. And I try to do that, and sometimes I just get super excited and I forget to add the extra word. Our Virgo friends help us all the time. I'm a dirty North American who only pays attention to things that happen in North America. Okay, so we have purple things on here. These are black holes that are detected by electromagnetic telescopes. That's what EM stands for. That's really just light. That's what we mean. There are black holes that we have discovered because of their influence on other stuff around them. The blue ones are the ones that we detected with gravitational waves. Similarly, you can actually find neutron stars with radio emission. So these are our electromagnetic neutron stars. And then there are the LIGO Virgo neutron stars in orange. Now, all of these things, in terms of how they're distributed on the X part, the horizontal part, that doesn't mean anything. The only thing that matters is how far up they are distributed. So if you see along the left there, there's a 1, a 2, a 5, 10, 20, 40, 80. That's how much mass the objects had in terms of the mass of our sun. We love our sun so much that we make everything be in terms of our sun. Now you can see that most of the neutron stars have something like the mass of like 1.2 to 1.4, kind of like I was saying earlier, of our sun. And when they merge together, they make something that's kind of like 2.4-ish. We're actually not sure what 2 neutron stars leave behind. We think at this point, it's taken us a while, but we think at this point it's probably a black hole that it collapsed down to. But there's actually still a lot of debate going on about that. Now in blue, these are the big whoppers. These are our black holes that have at least 8 times the mass of our sun, and some of them have almost 40, 36, 37, 38. Those are whoppers. That is a big black hole. And when they crash into each other, they make an even bigger black hole. So we now know that there are black holes that exist out in the universe that are something like 80 times the mass of our sun, which I think is awesome. Okay, so this is what we understood at the end of like 2018-ish. LIGO had turned off. They do something called observing runs. So in observing run 1, we had 3 black holes. In observing run 2, by the end of it, we had 11 systems to play with, which was cool. They turned off. Everybody did science. Everybody thought about it. Everyone was super hyped still about gravitational waves. And we actually could say something very specific. This is a beautiful image of 2 black holes that are orbiting each other. They probably have these disks of stuff that orbit around them. I love this image so much. Okay, so from LIGO's second observing run, there are really 2 things that we nailed down. Number 1, pairs of black holes, like the ones that I showed you on that graph, merge once every 5 minutes in the universe. There have been a lot of black holes that crashed into each other over the time that I've been yapping at you. That's wild. That's awesome. We now know this. That's great for people like me who want to know how many black holes there are in the universe. Because if I know how they come together because of Einstein's theory of gravity, I can actually count up how many, because I know how fast they merge, how many there are merging every 5 minutes in the universe. I can count up how many black holes there are. Spoiler, there's like billions of black holes in the universe. Yes, cool. Okay, next thing. Pairs of neutron stars merge once every 30 seconds. Holy moly, that is fantastic. We love that so much because that means that there are tons of neutron stars for us to observe as well. All of this is super cool and something that we could come up with only 11 gravitational wave events. Imagine what we're going to do for the next 200 years. Think about all of the things that happened in the first 5 years that we had telescopes. Probably not a lot. We like figured out where planets are and stuff. We kind of like, I don't know, 1600s and 1700s, we like learned about orbits. It took all the way until 1950 to even understand like how stars mostly work a little bit. In 5 years, we have figured this incredible piece of science out. Get excited for more. Okay, so on April 1st of last year, 2019, LIGO turned on again. And there's something really special about this last observing run that we've just been through. And that is that the previous things, they were announced in press conferences. People were kind of secretive because they wanted to be really sure that they were doing stuff right. We as scientists try to be really, really, really careful before we just come at you and say like, yeah, we found this cool thing, like everybody get excited. Oh, sorry, we were totally wrong. Because in science, it turns out that we're often wrong a lot more times than we're right. And so for all of the 12 gravitational waves that I just told you about, the LIGO-Virgo collaboration kept them secret to make sure that they were very, very positive that they had detected these gravitational waves. Now that they've shown us that they can do it for 12, they started literally tweeting. They tweet every time that there is a candidate for a gravitational wave. If you are a Twitter user, which I understand maybe some of you are not, but if you are, first follow me, Spacetime TV on Twitter, then follow Christopher Berry, because Christopher Berry is part of the LIGO scientific collaboration. And Christopher tweets every single time there is a candidate. And LIGO turned on April 1st, and then on April 8th, they had a candidate. Then on April 12th, they had another candidate. Okay, good first week, or good first 2 weeks, I guess. 21st, 25th, 26th. All of my friends, so disclaimer, I don't actually work in the LIGO-Virgo collaboration because they care about the stars that make the black holes, but I am obviously extremely hype about them. So during this period of time, all of my friends who work in this collaboration were like, holy cow, we're gonna get tired of this really fast because we've been in 3 weeks and we have 5. We've already made up almost half of everything that came in over 2 years. And the fun part is that LIGO didn't turn off. They kept coming. May 3rd, there was another one. I'll note here, Christopher doesn't just tell us that a gravitational wave candidate exists. He tells us probably what the candidate is, something like a binary black hole, so 2 black holes crashing into each other. He also says delightful, fantastic things like this. Will this event be your best friend? I hope that some of us will find best friends in these gravitational wave candidates. He also gives them ratings. Now be very careful with these ratings because they are not necessarily scientific. They are exactly what Christopher wants them to be at any moment. So if nothing else, just like follow Christopher to see his beautiful ratings. Okay, so we have another gravitational wave detection, sorry, I shouldn't say detection, candidate. They're always candidates until we publish a scientific paper about it. May 3rd, another one, the 12th, 13th, 17th. Really, the LIGO-Virgo collaboration people got tired. They keep coming, 19, 20, 21, really, for real. These detectors are incredible. These black holes merge all the ding dang time. It's awesome. Neutron stars, maybe a little bit less so. We can talk about why that is. The secret is that we can't see them quite as far away in the universe, and we can see the big black holes really, really far away. Oh man, they keep coming. On June 2nd, there was another one. I gave a talk on June 2nd, and that's why I stopped. And I'll be honest, after June 2nd, I totally stopped counting because like it gets a little bit tiring after like 20 of these things, like taking screenshots of tweets and stuff. Luckily, LIGO didn't turn off. Neither did Virgo, neither did Christopher. And just after they've turned off, we have something like 56 candidates of merging black holes, merging neutron stars since April 1st. We even have some candidates of neutron stars crashing into black holes, which is fun. That's even kind of different science. What the heck happens when that happens? We're not totally sure. There's a lot of people who write down theories who could, you know, want to sell you something. Just kidding. We don't sell science, but in any case, 56 events since April 1st, 65 events in total, 65 events in 5 years. This is crazy because our detectors aren't even at full sensitivity yet. They will be getting to full sensitivity over the next few years. And soon we're going to start to have trouble keeping up with all of these detections. So what's going to happen over the next few years, excuse me, over the next few years? Well, A, we wait for the LIGO detectors to be upgraded to their final sensitivity. And B, while we're hanging out in all of our houses, what's going to happen? Well, all of my friends in LIGO are going to be working. They are going to be working super hard, like we see our little gray friend here. And they're going to be publishing papers, and they're going to be telling us all of the gory details of these black holes and neutron stars that are crashing into each other. They're going to write papers. They're going to make sure everything looks good. And while that's happening, there's going to be people like me and my theory friends who say, guess what this tells you about stars? This tells you that there are more 100 times the mass of our sun stars than there are 200 times the mass of our sun stars. But honestly, your guess is as good as mine of what we're actually going to find out, because we don't have the data yet, but it's coming. And so I'm super, super excited as somebody who cares about the stars and cares about learning about these dead stars with gravity, because the future is going to be loud for us who do gravitational waves, not bright because we are finding dead stars to tell us about how stars live. And with that, I'm going to go to questions, and I hope that you guys on the chat have lots of questions for me. Yes, you do. Okay, great. Cool stuff. First thing, how are the locations for LIGO chosen, and Virgo? The locations for LIGO and Virgo are chosen kind of like 50-50 science reason and 50-50 funding reason. So I don't know so much about Italy's funding, but I can tell you about the United States' funding. And the reason that there is a LIGO detector in Washington and in Louisiana is, number one, that's kind of like as far apart as you can put them in the United States, which is good because we want to make sure that we're testing gravitational waves in this part of the United States and in this part of the United States. The other reason is actually because senators petitioned to have that science industry in their state. And honestly, science industry in your state is just like fantastic, because there are lots of extremely well-paying jobs to do this kind of work. And it's the kind of work that helps fuel future science research. So that's mostly how we choose it. Okay. Next one. If there are so many black holes in the universe, why are we not detecting gravitational waves all the time? Awesome question. The main reason is that our detectors are not sensitive enough yet to observe them. Our detectors can only see a certain gravitational wave to a certain distance away. If it's a really strong gravitational wave, we can observe it if it occurred a lot farther away than if it's a weaker gravitational wave. So neutron stars crashing into each other don't have a lot of mass, so they don't create as big of gravitational waves. So we can only see them to something called like 100 or 200 megaparsecs. That's weird, crazy astronomer units. But that's 1,000,000 times 3 times a light year, which doesn't make any sense, but we can only see them to a certain distance. Black holes, we can see out to billions of this. So if you're thinking about 1,000,000 parsecs versus 1,000,000,000 parsecs, that means that the volume that you can see black holes in is just enormous relative to what you can see neutron stars in. And if there are black holes that are even farther away from that, we need to get more sensitive detectors. So that's why we haven't seen all of them yet. Fear not, we are trying to build the most sensitive detectors so that we can see every black hole that ever merged in the galaxy, or not in the galaxy, what? In the universe. Okay, next question. From my cousin, work. Okay, do black holes stop producing gravitational waves after they crash into each other? Totally great question. Yes. Once a black hole crashes into another black hole, unless it finds another neighbor, which sometimes we think they can, it will not emit gravitational waves. So just one object hanging out doesn't emit gravitational waves. If you are just a spinning thing, you're not going to emit gravitational waves. If you're me, like doing this, I'm emitting gravitational waves because I don't have something called a symmetry. So I'm not a perfect circle. A single black hole is a perfect circle. Okay, great question. So this is correct. Black holes do not produce gravitational waves after they crash into each other. Next questions. Do the lengths of the gravitational waves have anything to do with the black holes crashing into each other? They totally do. This is how we know what kind of black holes they are when they crash into each other. The shape of the wave tells us how fast the two black holes are that crash into each other and how much mass they have. We only know that because we know the shape of the gravitational wave that they make, and then that's what we observe. So we have theories that tell us a 30 solar mass black hole and a 20 solar mass black hole make this shape. And we actually have to just compare to all of our different models and find which one matches the best. Okay, great question. What happens if a neutron star merges with a black hole? I kid you not, there are academic papers that are coming out like as we speak that disagree with each other on this. Some people think that if you crash a neutron star into a black hole, you can rip the neutron star apart before it falls into the black hole. Some people think that it just falls right in before it has time to rip apart. If the neutron star can rip apart before it crashes into the black hole, then you emit light and we can point telescopes. So every time that there's a trigger that says, hey, LIGO and Virgo say that there is a neutron star that crashed into a black hole in this direction, all of my friends who point telescopes there to see. We don't know yet. We haven't observed it yet, but we might know in the next few years. Okay. We have 2 more questions. Can the signal be detected early enough so that neutron star mergers can be observed visually? Yes. So we observed the neutron star video that I showed you. We actually watched this happen. We saw it in every kind of telescope that we have here on Earth, which is incredible. We observed it with a gamma ray detector, like a second or so after we observed the gravitational wave merger. That actually tells us something that we were really interested to know, which is gravitational waves travel basically exactly at the speed of light, which is cool. And then because we knew about the gravitational wave, literally, like I have friends here in Toronto who were like calling up their buddies being like, hey, people down in Chile, point your telescopes over in this direction because the gravitational wave detector told us where it is. And I'll get to the next question down, which I think is the last question about this. And ooh, I'm getting more questions. Yes. Okay. So basically, we have totally observed neutron star mergers. We know what happens when they crash into each other. We have observed the light. It is beautiful. We love it. Okay, how do we know the location for each event? We know the location because gravitational wave detectors are also kind of like our ears, and that we use sort of like echolocation. So if the detector in Washington sees the wave first, then it hits Louisiana, then it hits Italy, we know that it's coming from a directional path from the Earth. That's the only way that we know the direction. So when we tell our friends who point telescopes, who like point on little teeny tiny points in the sky, we'll tell them like, hey, look in this like quarter of the sky. And then they all get annoyed because their telescope, you'd have to point their telescope like 10,000 times to look in the sky, like to fill out the entire region that we tell them that the wave came from. Luckily, there are only galaxies that populate certain parts of that region, and so they can pick, and everybody splits up and points telescopes at different galaxies to see if they can catch it. We were extremely lucky to catch the first neutron star merger. We haven't observed light, as far as I know, from another merger yet. Okay. Let's see. All right, we have one more question, and wow, it is 8:08, which means that we should probably start like ramping this bad boy up. So I'm going to answer this last question, and if you have any more questions, please absolutely follow me on Twitter, SpacetimeKatie. Cool. Okay, last question. At some point in the distant future, could all the black holes be combined into one? This is a fun idea, maybe. I don't know if it's fun, but I think it's fun. So the reason that I don't think that this will happen is because space is flippin' enormous. So if you think about distances in space, for the black holes to all merge together into one eventual like big monster black hole that like eats up the whole universe or whatever, the black holes would have to be close to each other. And when you think about that, it actually kind of doesn't work in space because number one, space is big. Most things are pretty far apart. Our next closest star is 3 light years away from us. The closest black hole that we know of is like 10,000 light years away from us or some nonsense, like super far away. So they probably are not going to all merge into each other. The other reason is because the universe is expanding We know that the universe is expanding. There's nothing to tell us that the universe is actually going to stop expanding. We also know that it's actually expanding faster and faster and faster every second that I yam or on and chew. So eventually the expanding universe is going to win out and there will be no black holes merging into any other black holes. So sorry for that. Yeah, okay, cool. This ends the, I don't know what installment I am, 4th installment of Cosmos from Your Couch, put on by the Dunlap Institute. My name is Katie Brevik. I've been your host for this evening. I work at the Canadian Institute for Theoretical Astrophysics. I am grateful to them for providing me a job that allows me to do science and talk to the wonderful people like you who have watched here on YouTube. If you enjoyed this, tell your friends to watch and tell them to tell me how cool it is on Twitter, because I am vain and I love that. We have so many more of these coming, so please tell your friends. This looks like this is going to happen every Tuesday and Thursday for the next at least month or so. So please come back and watch these. We have an archive on the Dunlap Institute YouTube for you to see a few other talks that have already come. Thanks again for joining us. Thanks for letting us share our science with you. And I hope that y'all have a fantastic rest of your Thursday evening. Thanks.